This episode of Fluid Power Forum is sponsored by IFP Motion Solutions Incorporated, the leader at engineering electronics into fluid power distribution. IFP spans the 13 central states from Minnesota to Texas. For more information, visit ifpusa.com. Also, this episode of Fluid Power Forum is sponsored by Endeavor AI. Endeavor AI automates order entry, quoting, and the quote-to-cash process. Win more, sell more, and save time, all without adding headcount. Head to endeavor.ai to learn more. Welcome to Fluid Power Forum, a podcast of the National Fluid Power Association. I'm your host, Eric Lanke. It's my job to interview interesting people who are moving fluid power technology forward. If you'd like to be part of the show, you can follow us on LinkedIn. You'll find us on LinkedIn at the National Fluid Power Association. And make sure to keep sharing those interesting and innovative uses of fluid power with our hashtag, #OnlyFluidPowerCan. If you see an interesting application of fluid power, you want to learn more about it, share it on social media. Use that hashtag #OnlyFluidPowerCan. We'll see it, and you just might hear it discussed on a future episode of Fluid Power Forum. Also, please subscribe to our show. You can find us on Apple Podcasts, or on Spotify, or on a lot of the other popular podcatch and services. Hey, wherever you find us, please subscribe to the show, and then give us a quick rating. Those ratings really do help promote the show and allow more and more of our friends in the industry to join in on these important conversations. My guest today is Barun Acharya, the System Engineering Manager for Electrification at Parker Hannifin. Parker was founded over 100 years ago, first focusing on pneumatics, but has since expanded into a global powerhouse manufacturer of just about every component across the full spectrum of motion control technologies. This episode is the next one in a short series that we're doing on the topic of a recent white paper we published, Energy Efficiency Gains from Electrified Hydraulics. And Barun participated in a technology conference that we hosted at CONEXPO on that topic. And so we invited him into our forum to discuss key ideas related to the electrification of fluid power systems. So Barun, welcome to Fluid Power Forum.
Thank you, Eric. Glad to be here.
I'm happy to have you on the call. I really enjoyed the presentation that you gave at the CONEXPO show a few months ago, and want to learn more about that. Tell our listeners a little bit more about yourself, though, if they're not familiar. What is your background, and how did you find yourself coming to work at Parker Hannifin?
Absolutely. So my background is mechanical and hydraulic systems, and basically I started my career as designing hydraulic components, low-speed hydraulic motors, steering, brakes, and then hydrostatic pumps. That's kind of my base, if you would. And then from there, I started working into mobile machinery in terms of hydraulic systems, putting systems together, and then ended up in electrification by accident, more because our customers kept on asking, how can I electrify this machine without braking? And my peers pushed me because I like new challenges. So that's kind of how I got into electrification. And if I have to sum up, hydraulics taught me how machines create force, and electrification taught me how machines manage energy. I mean, basically both are motion control problems. It's just the energy source change. The physics is still the same.
Yeah.
And that's kind of the base. And today I lead a systems and applications engineering team at Parker in Motion Systems Group. And these are the people, we are sitting at the intersection between electric components, hydraulic systems, and controls.
Yeah. I was going to ask about when did this all start, this electrification thing, especially at Parker? I mean, Parker's been in the motion control business for a long time. And you said you kind of fell into it initially, if I heard you right. Hey, we've got this crazy idea. We needed to work on something. Is that what it was? Or
Yeah, I mean, to be honest, it's really the customers who pulled us in.
yeah,
And I think some of the reasons behind that were like the emissions deadlines. So you have the tier emissions regulations in North America and the stage emissions in Europe. Then urban noise rules, indoor job sites, if you would, and then the ESG mandates that all the different fleet customers have. And those are really the main reasons why Parker was pulled into electrification.
yeah,
And then one thing we found is it just so happened, not too many people know, Parker had a industrial motors, inverters, components, that portfolio that was already there. So
sure,
Parker was already well known in that. And also so that's on the industrial side. And on the mobile side, the Parker Aerospace was very strong. So if you have some of the high-end military, that was already running with electric actuators. So Parker was already
right.
heavy side as well. So the goal was to bridge the two together, and then our group, the top leadership, they came up with a team to meet this customer demand and to come up with a solution for the price point you'll have on the construction mobile market, if you would, for electrification.
Yeah, I remember the days when the industrial and the mobile parts of Parker were in competition with one another. They were two different divisions, right? And now they've really come together in what, Motion Systems, is that what it's called now in Parker?
Yes, it's called the Motion Systems
Yeah,
Group.
right. And so when you say the customers really brought this to you, so they were busy electrifying the power sources on their machines in order to comply with these mandates, if you will, right? To lower the energy usage and to lower the fuel emissions and things like that, right?
Correct.
And then, so you still needed, then Parker and many other companies needed to figure out, do we keep hydraulics on these machines and marry it better to these electric power sources, or do we switch to some electrically actuated or electromagnetic? And that's really what you're talking about. Like, that's the key challenges that you've been facing. Are there other challenges that you found yourself up against as you went through that transition?
Yeah, so some of the key challenges that, once we started working on this was, if I had to bucket them, number one would be the duty cycle problem. So basically,
Mm,
it was almost a universal problem, if I had to say. Most OEMs really didn't know what the machine was doing, at a finite level, or minute by minute, if you would.
sure.
So basically, it was, and also the usage of the machines is also very different, I must say. It's not like a vehicle, driving back and forth. So the duty cycle is much more defined.
Yeah.
Hydraulics by nature is much more nomadic in nature, the duty cycle. So,
Yeah.
so to me, number one problem was the lack of knowledge about the duty cycle. So we came up with a process, what we call energy mapping, where we would instrument the vehicle and kind of come up with how the customers, or some of the edge case customers, are using this OEM machines.
Mm-hmm.
So that's the number one challenge. I think the number two challenge in terms of electrification was the power density mismatch. So one thing people forget, like you said, many people would love to eliminate hydraulics, but the hydraulic actuators, the
Not,
power density
not,
is so
yeah.
high.
I just got to say, not me, Barun. I don't want to eliminate any hydraulics anywhere, but go ahead, please.
Yeah, so the hydraulics power actuator is like 5 to 10 times more than the electric actuators.
Right.
So you have to be careful which ones you want to replace. Replacing a cylinder, you're probably going to lose all the time. So, but if you want to replace an engine and keep the hydraulic system and the cylinder, then you win.
Yeah.
So that's kind of the other challenge, if I would, you know. And then the third challenge I would say is the system integration. The hardest problem is really not the component selection. It's how you integrate together. You have the CAN networks, the CAN coordination between all these different components. And then, of course, there's software on top, the software arbitration, the transient response, how you're going to do the AMC because of the electrification. And then last but not least is the operator field. So all the subsystems, they have to work seamlessly, and it should be connected properly.
Yeah.
So people forget, how big a system problem this is, system integration problem it is.
Sure.
And then the last point I must emphasize is the noise. So I don't think the industry talks about the noise. When you remove the diesel,
Yeah.
You really reveal all the noise sources that has been acoustically masked, if you would,
Right.
for many, many years. And to be frank, a piston pump whine, a 9-piston pump, for example, running at 2,200 RPM.
It's a unique noise. Yeah, exactly. Yeah.
Yeah,
Right.
30 hertz. It's just hitting you at the worst part of the hearing sensitivity. So it's really so when people say that electric is just quieter, they're just they're just missing the operator experience, or just lying, So there's this unique challenges as well, that you have to recognize and you have to address.
Well, and the solution, if you will, to a lot of those challenges, to oversimplify it, is new architectures for the hydraulic system, like new ways of putting the components together and to control them effectively. At the talk that you gave at CONEXPO that I mentioned, you broke down some of those new architectures and some new hybrid architectures that Parker's been working on. Can you tell us a little bit more about some of the characteristics, maybe opposed to the more traditional structures that we've seen?
Yes, absolutely. So I think I need to be precise here because this is the NFPA. The listeners, here, they know modern hydraulics.
Sure.
So I have to be careful here. The inefficiency in the traditional architecture really isn't the hydraulic circuit, to be honest, because remember, my background is also hydraulics. So if you design the system right, with a variable piston pump, with load sense, or EDC, electric displacement control, the D-strokes, and then the modern valves with all the compensation. The hydraulic side is not the issue. The issue is the structural inefficiency, if you would, between the engine and the pump, the coupling there.
Right.
That is the issue because, the diesel runs at a fixed speed, which is dictated by the worst case, your actual demand, if you would. So you want to run it at that 2,300 RPM, if you would. And even if the operator is doing nothing and the pump is fully distroked, the engine is still spinning, burning the fuel, overcoming its friction and all that. So basically, the engine is always sized for this peak and running at this peak RPM, even if it's doing average work or no work.
Mm-hmm.
Me, that is the gap, So with electrification, the opportunity in terms of architecture is how do you decouple the engine from this pump demand, if you would, and that's kind of where we get and then the smart hybrid. What it does is it changes the topology to address this. So basically, how we do that is we run the engine at this, the BSFCs, the sweet spot, if you would.
Yeah.
The brake specific fuel consumption, the sweet spot, almost like a genset, if you would, and then the battery is there to buffer, for this certain demand mismatch, if you would, and so basically, to recap, in a traditional architecture, the engine is seeing every load transient, if you would, but in a smart hybrid, the low transients are taken by the battery pack, the small battery pack first.
I see. Okay.
And the engine doesn't even know it happened. So engine only sees this flat demand. It's not looking at this sawtooth, the actual demand from the application, if you would.
So in this case, the hybridization is really on the prime mover side of the circuit, right? So it's a coupling of an engine with a battery to provide the right power to the pump at the right time for the actuation, right?
Correct.
Yeah.
Correct.
So where are there particular applications or particular machines where that architecture is best used? Where do we see this occurring?
Yeah, so basically the way we look at it, or at least our team looks at it, a simple way to frame would be look at any OEM application and break it into like a 2x2,
Right.
average power on one axis, if you would, and the utilization on another. So if you have a low average power and low utilization, so imagine a small machine that runs for a few hours, think like a mini excavator, compact loader. So something like that, you can make it fully battery electric, so it's not an issue. So that's one end of the, so 2x2 matrix, if you would. So you're looking at one side is that. And then the other end is going to be high average power, high utilization. So imagine a big, big excavator that's running in a mining application or whatever, big horsepower,
Right.
running 20 hours a day, if you would, and the load is almost 100%. So in that case, diesel always wins. So on the low side, fully electric wins. On the high side, the diesel wins. The problem is the other two quadrants, if you would. So imagine a high average power and low utilization, like a backhoe loader, where you have peak power events, when you're digging, but most of the time the machine is idle, if you would, or a low average power and high utilization, like a refuse truck or port equipment, where you have, modest power demand from the machine,
Right.
but it runs all day with a lot of start-stop, if you would. So in these two quadrants is where the hybrids thrive, if you would. So otherwise, fully electric, ICE. So I guess my thesis is there's place for everything. And again, the rationale why is because of the cost of the batteries. And then remember, at the end of the day, we are being paid by a customer to do work, so we cannot just load up a piece of equipment, a work equipment with batteries, because now the weight of the batteries are so high and the cost is so high that we're not going to have an economic solution for the customer. So that's kind of the reason why this hybrid makes a lot of sense.
Yeah.
And then there's one more point I should say.
Okay.
The energy recovery is the other piece. So you can, with a traction, you can do some regen. If there's a swing, you can do some regen. So that's the other piece, if you would, that helps.
We'll continue with our guest in just a moment, but first I want to tell you about an opportunity to engage in the future of fluid power technology. Two of NFPA's most active committees are our two technology task forces, one focused on mobile applications of fluid power, the second on industrial applications. Each of these task forces work on a series of projects that help us better understand the technology trends in these sectors and help us develop the resources and connections that will be needed to keep fluid power positioned as an actuation technology of choice on both mobile and industrial platforms. The Mobile Task Force publishes a series of reports. Their latest was on ways to design more energy-efficient fluid power systems for mobile equipment with electrified prime movers. The Industrial Task Force also publishes reports. Their latest was on ways to minimize and prevent leaks in fluid power equipment. And they have also completed a year-long project that created an independent technology roadmap specifically for fluid power in industrial applications. All of these resources are accessible on our website at nfpa.com/technology reports. But more important is your ability to participate on and engage with the technology professionals that serve on these task forces. New working groups are forming now around the use of sensors and data analytics in fluid power systems, as well as many other cutting-edge technology advances. These task forces are a great example of NFPA's effective forum in action, with NFPA members across the supply chain and an increasing number of their OEM customers actively engaged in creating the technology strategies that help all of their businesses grow. To learn more and to get involved, contact me at elanke@nfpa.com. Yeah, I mean, again, you're really stressing the need for a kind of more of a systems level approach to what you're putting together there, and there's a lot of new technologies, if you will, that are finding their ways into the systems. I know you talked about some of these in your presentation. One was the use of advanced sensors and data collection. Can you talk a little bit about where we're seeing that come into the situation?
Absolutely. Um, I think one of the key points is you cannot optimize what you cannot measure, if you would,
Right. Yeah.
So typically what happens in in a typical legacy industry, if you would, we may have a pressure transducer on the main pump or a tach on the engine, and that's about it, So, but with electrification, we get a bunch of data for free, Say, for example, the inverter is a sensor.
Mm-hmm.
So I know my pulse voltage, I know my phase currents, I have an estimate on the torque, I know all the junction temperatures on the IGBTs, so I know every motor speed, position, the thermal condition, the battery BMS is telling me the SOC, the health, cell level data. So basically, you have all this other information that you have. And basically, what that does is that helps me in optimizing the system, the hydraulic system. Because typically, if you look at a traditional system, I would say the hydraulic systems are over-engineered. We're like, let's add, if you need a 20 cc pump, we're like, oh, let's put a 30 cc pump, bigger is better.
Mm-hmm.
We're going to just run the engine. But with electrification, because I know exactly what's going on,
Yeah.
I can really design the system exactly what the needs are. And because of all this feedback from the data, from the sensors that we get, free data, if you would.
Is there any like machine learning taking place on the machines with all of that data flowing around?
Yeah, absolutely. I mean, it's not like a chat GPT, writing a
Right.
prompt code, if you would. So to me, machine learning is more like a pattern recognition is what's going on
Yeah.
from a operator's signals operator standpoint, if you would. So one would be like, imagine, like a duty cycle classification, if you would. I can train a model that's looking at the pressure, position, and the accelerometer meter data and recognize, what the machine is doing. So whether it's digging, lifting, or in transit, if you would. So I can train my model, and then based on that, then I can train the model. Hey, if this is what's going on, then recognize this is the state or this is the duty cycle classification that's doing, and then I can ask to spin the pump in a certain way, warm up the inverter if you would, pre-charge it this way. So there's different things it could do based on what it's doing. So that's kind of one of the key things with machine learning.
Yeah.
And then the second thing would be, I would say, is the predictive maintenance, because, so if I have a IGBT issue or, I would know beforehand what's going on, if a pump is going to go wrong. So these are more active research going on, if you would.
Yeah.
So machine learning, it can catch, before the warranty call, it can tell you, hey, you need to start thinking about replacing this motor inverter or the hydraulics, the pump signature is making some cavitation issues. So that would be the second thing. And the last thing I would say is also the operator coaching.
Sure.
So I can also the VCU knows how the operator is working or fighting the machine, if you would, and if they are over pressurizing, doing something that we don't like, I can have adaptive controls where I can start limiting the power of the machine. So kind of coach the operator to more utilize the machine in a more optimal way, if you would.
Yeah. As you're describing this, Barun, it's interesting to me that, like, if I can paraphrase this right, the impetus for all of these changes on these machines was in search of greater efficiency. And it's these technologies themselves that are providing that, right? In a way, right? It's because it's electrified now. Suddenly, there's these opportunities to make something more efficient than you could before in a traditional architecture because of all of this new technology that's on the machine. Is that the way you see it, or that's the way it strikes me?
Yes, absolutely.
Yeah.
I think. I mean, first of all, back to the last question on to me, machine learning, it doesn't fix the energy waste; it finds it.
Yeah.
Still comes with the architecture,
Yeah.
So, whether I'm going to have a heat pump, or I mean, how I'm going to classify the system, if you would.
Right.
And then from a systems level, I mean, you have to approach it a little different. It's not just pull out the engine, put a motor. I think before we used to do it more like I don't know, like a potluck dinner, So you have the engine team comes in with the knowledge of the diesel. The hydraulics team comes in like, hey, I got the valves and the cylinders. The controls guy goes in, okay, I got the joystick and then the controller. But the systems level thinking to me is we have to kind of plan the whole menu together from scratch at the very beginning. And to me, that is the key difference, if you would.
Yeah, if I remember the presentation that you gave a couple of application examples of a lot of these technologies in the real world setting, if you will, and talked about some of the advantages of for that particular machine. I wonder if I can ask you to maybe pick one of those examples. There's one about a backhoe loader, one about a refuse truck, and one about a highly hybrid compact construction machine, if I remember right. But pick one of those and tell us more about how these things happen on a real machine and what advantages they get.
Absolutely. Let's talk about the hybrid backhoe loader because that happened during. So basically, the objective there was we downsized the engine from 75 horsepower to 49.9 horsepower, and the reason was if below 50 horsepower. The part of the world where this was used, it would need a lower emission standards. So we saved a lot of energy, a lot of money on the engine side, if you would.
Sure.
So number one objective was to downsize the engine. Number two was on the hybrid backhoe was the need to run this in the excavator mode. It needed to be run only in electric. And the reason was they wanted to operate this backhoe in an indoor condition where obviously you can't have the IC running for a long time. So they wanted it fully electric. So it's low noise and zero emissions. That was the goal.
Yeah.
And then the third goal was to capture the government incentives because of, having this hybrid option with this fully electric indoor operation. And the last but not least, the big requirement was you have to run the same machine, so the same form factor, without any changes, without any growth in the machine, if you would. The goal was all they did is took the backhoe, put in the smaller engine, and now make it hybrid and make it functional with the same form factor. And we were able to achieve all those goals with this hybrid solution that we had.
That's great. Yeah. So these examples, I'm thinking back to the 2x2 matrix that you described for us, to try to figure out like where does this technology, what kind of machine and what kind of duty application makes the most sense. Do these examples fit into those two quadrants that you described?
Yes.
And
yes, absolutely. So this is what I would call the high average power and low utilization,
right.
In the application, or low average power, high utilization. So it depends, a backhoe loader in North America is used very differently, unlike a backhoe loader in India. So just so you know,
Sure.
But
right.
it falls into one or either of these quadrants, and it meets the requirements that we have for the hybrid solution that we came up with. And basically, our solution basically showed that we could lower the engine size and also cut down the fuel by 15%, for the same productivity, if you would.
Right.
And then we also came up with what we call a hybrid productivity factor, some method, because, some part of the world, the cost of the fuel matters, and some part of the world, the cost of the operator matters. So
right.
if you want eco mode, you save fuel. If you go to full power mode, then you don't, you save on productivity. You get the job done quickly.
Yeah, right. So what do you, are there, my sense is that these technologies coming into the marketplace, we're just beginning to see this happen, right? There must be a lot of other opportunities. Can you predict for us or tell us like where we might start seeing some of these technologies? What kind of machines, what kind of applications?
Yeah, I think, I mean, to be frank, in North America, we were going really full speed with electrification, but with the new administration, things have taken a little backseat.
Oh yeah.
But in Europe, in Asia, things are looking really good. So there is, cost of fuel lately with the crisis in Gulf and all, things are helping again. So
Sure.
you may not see it here, but the rest of the world, electrification is going up. So the S curve that we say for adoption, so in US might be more to the left, but the rest of the world, it's really picking up. And in terms of applications, ground support equipment, like ports, both the airport, seaports,
Sure.
material handling there, underground mining for sure because of the added cost of ventilation, and then even on-highway work trucks, where you could cut down all the idle time, terminal tractors. So these are some of the applications, some in ag, and then even ZTR mowers. So there's all these different applications that we're working towards, and it's just delayed, I think, the adoption of electrification, but it's not, it's going to happen.
Yeah.
It's just by a few years.
Yeah, I mean, a lot of the market forces are still there that are demanding these kinds of solutions. So, what about the electrification technologies themselves in terms of the future? Are there new developments that we would expect to see on that space? Does Parker have a skunk works where they're working on new designs, or what do you think is going to happen next in that area?
I think from Parker's standpoint, we are completely, we're putting our lot of energy in electrification,
Yeah.
and hence the acquisition of Curtis that happened, September of last year, and then we're still incorporating them within Parker Corporation. And Curtis has this inverter knowledge, traction controls, a lot of new stuff with the high voltage. They were already known in the low voltage side. A lot of people don't know what they're doing on the high voltage side. So there's a lot of new products that's going to be online in the next 12 to 24 months.
Yeah.
That customers are going to be excited about. And I think long term, in terms of my prediction, would be I think hybrid is going to be, is going to be used more and more short term. I mean, it's going to be incorporated. It stops being a category, if you would. Every mobile machine, I think, is going to have battery electric, hybrid. Those are the different options you're going to have by default, if you would.
Yeah.
I think hydraulics is going to become more into electrohydraulics because of electrification. So those would be my prediction. I mean, to me, at the end of the day, the future of fluid power is not just fluid power versus electrification. It's going to be more fluid power because of electrification.
Yeah. Right. Yeah,
that's what I see.
That's a good way of phrasing it. And we're certainly seeing, companies across the industry taking on these technology challenges, incorporating these electric technologies as part of their portfolios, like Parker is doing, but many others are doing it as well. So it's really redefining, what we think of fluid power, like what components are needed for a fluid power system. Well, now inverters are definitely part of that system, right? So,
absolutely.
Yeah.
Electrification doesn't replace fluid power. It basically lets us finally optimize the machine around the work cycle rather than around the engine. So that's my experience working on electrification for the past 15 years.
All right. Well, that is a great way to wrap up this episode of Fluid Power Forum. My thanks again to Barun Acharya, who has been my guest on this episode. If you want to connect with him, the best way to do that is to send him an email, and we're going to put a link to his email address in the show notes for this episode. While you're online, make sure to check out NFPA's full white paper on this exciting topic. We called it Energy Efficiency Gains from Electrified Hydraulics, and you can find it on our website at nfpa.com/technology reports. And remember, if you like our podcast, and we hope you do, please follow us on LinkedIn. You'll get all kinds of updates there about the show and about NFPA. We're on LinkedIn at the National Fluid Power Association. And make sure to keep sharing those interesting and innovative uses of fluid power with our hashtag #OnlyFluidPowerCan. It's a great way for you to let us know the kind of topics you want to hear addressed on the show. Fluid Power Forum is a podcast of the National Fluid Power Association. I'm your host, Eric Lanke, reminding you to join us next time in the forum.